next time you get a chance, look up at the night sky. The chances are the view won't be quite as spectacular as this. This amazing photo was taken by my colleague Oscar on an observing run on the island of La Palma in the Canaries. But even in the UK, on a clear night, you can see many stars. Now imagine each of these stars surrounded by planets teeming with life. Imagine what it would be like to know, not just to speculate, to hope, or maybe to dread, but actually to know that there's life out there. It would be humbling and exhilarating at the same time. Our lives would probably go on mostly unaffected, but at the same time, it would completely change the way that we think about ourselves and our place in the cosmos. Now, despite occasional reports in the news from UFO sightings to bugs on Mars, no one's actually found solid evidence of life on another world yet. But I believe that we can find such evidence, and what's more, I believe it could happen relatively soon, in the next 20 or 30 years maybe. And that's because in the last 30 years, we have found thousands of planets orbiting around other stars. We call them exoplanets. Some are unbelievably alien, but some are what we call habitable, which means that their sizes and their temperatures are such that we think life could arise there. Still, when I say that I believe we can find evidence of extraterrestrial life during my professional lifetime, I am taking a risk, because I don't know that such life actually exists, and nobody does. Nobody will until we actually find it. The idea that other stars are like the sun and have their own planetary systems and may even have life is far from new. The Roman philosopher Lucretius wrote about it in beautiful Latin verse and in startlingly modern terms back in 50 AD. This photo is of the oldest surviving copy of his poem On the Nature of Things. Many other philosophers continued to discuss the idea ever since, and over the last century or so, astronomers started looking for exoplanets in earnest, but it's not until around 30 years ago that we began to find them. So why did it take so long? Well, astronomers rely almost exclusively on light to study the cosmos, and planets emit next to no light of their own. So mostly we find planets indirectly through the effect they have on their stars. And the first exoplanets were detected because of the motion they induce in their star. So both the star and the planet orbit around a fixed point in space we call the center of mass. In this animation, the motion of the star has been vastly exaggerated so that you can see it. In reality, we can't detect it directly, but imagine now flying so that we're closer to the orbital plane of the planet and zooming in on the star. The star moves towards and away from us as it wobbles in its tiny orbit. When it moves away from us, its light is shifted towards the red. When it moves towards us, its light is blue shifted. This is called the Doppler effect, and you've all experienced it when an ambulance rushes past you in the street and you hear the pitch of its siren change. Here, the color change has also been grossly exaggerated. In reality, the color only changes by a few parts per million, but amazingly, that is something we can measure using specially designed spectrographs. It's the development of those spectrographs that enabled the first exoplanets to be detected in the 1990s, and they've continued to improve ever since. So today, we can look at a distant star that's a ball of hot plasma 1 million kilometers across, located tens or maybe even hundreds of light years away, and we can tell if that star is moving towards or away from us at the speed of a person walking. It never ceases to amaze me. The other method I want to introduce to you today is the transit method. A transit happens when a planet passes between us and its star, so we have to see the orbit perfectly edge-on. When that happens, if we monitor the brightness of the star, we will see it dip a little bit as the planet blocks out part of the star's light. A planet like Jupiter blocks out around 1% of its host star's light. We can actually detect that using relatively small telescopes from the ground. And the first exoplanet transit was detected in 2000, just as I was about to embark on my own astronomy journey. The first exoplanets found had masses and radii sizes similar to Jupiter, but they orbited much closer to their host stars, completing their orbits in just a few days. Planets on such orbits are what we call tidally locked. They always show the same side to their star, just like the moon always shows the same side to the Earth. Their day sides are incredibly hot, hotter than the surface of some small stars, but their night sides can be 1,000 degrees colder. And that sets up hugely powerful winds that circle the entire planet. Only around 1% of stars have a hot Jupiter, but because they're so easy to find, we found them first. And today, we can study them in amazing detail, even though we can't ever see them. If you follow science news in the media, you will have come across the James Webb Space Telescope. With a pristine mirror 6.5 meters across, it's every astronomer's favorite new toy. And it's produced some beautiful images, but the most exciting results from JWST for someone like me are plots like this one. Taken by observing a transit of a hot Jupiter. When the planet passes in front of the star, its atmosphere filters a tiny fraction of the star's light. And gases in the atmosphere of the planet absorb an even tinier fraction of that light, so that the planet appears bigger at some wavelengths than at others. These JWST observations have revealed the cocktail of molecules present in these exotic planets' atmosphere in unprecedented detail. But ever since we found hot Jupiters, we also wanted to push our detections to smaller planets and planets on wider orbits, more similar to the planets in our own solar system. But the Earth's diameter is 100 times smaller than the Sun's. That means that during a transit, the Earth blocks out only 1% of the Sun's light. And that's too small to detect from the ground. We have to go to space. So in the 90s, space agencies started to plan missions dedicated to staring at thousands of stars for years on end in order to catch those tiny blips. In 2001, I spent 6 months working for the European Space Agency, and I was assigned to such a project and tasked with writing computer programs to detect those transits. And I loved working on that problem so much that I continued doing it for my PhD in Cambridge. Even from space, it is a hard problem because I haven't been completely honest with you. A real star actually looks more like this. This movie was made by taking images from NASA's Solar Dynamics Observatory every 6 hours for the month of January this year. And you can see these dark spots. They move from left to right across the screen as the sun spins. It spins once every 27 days. These spots, we call sunspots, they're regions on the solar surface which are cooler than the rest. They're caused by strong magnetic field. And they themselves can be larger than the Earth. So when we monitor the light of a distant star, star spots like these cause variations which are much bigger than the transits we're trying to discover. But we can use clever data analysis techniques to separate the transits from the star spot signals. That's what my PhD was all about. And I was really pleased with myself, because by the end I could show that these missions we were working on would reach their goals. They could find Earth-like planets. And then do you know what happened? The mission I was working on was cancelled. It wasn't anything personal. It wasn't even scientific. It was just a case of budget restrictions. That sort of thing happens in space sector sometimes, but it was a bit of a blow to a budding young scientist like me. Luckily, in 2006, the French space agency, CNES, launched the Corot satellite, which was a smaller space telescope with similar, if slightly pared-down science goal, and I was able to repurpose my skills and my tools for that mission. Corot found the first transiting rocky planet. It's only 1.6 times larger than the Earth, but it completes its orbit in 20 hours. That's right, you heard me correctly, 20 hours. Its year is less than one of our days. We found it despite the fact that its star is much more spotty than ours, and the star spot variations are much larger than the transits. The planet is so hot that we think its day side is covered in a molten magma ocean that's evaporating straight out into space. We call it a lava world. In 2009, NASA launched the Kepler Space Telescope, which had a bigger mirror and a longer baseline than Corot. So that was the machine we'd really been waiting for, and it found thousands of exoplanets. I could spend hours telling you about all the weird and wonderful systems it found. But for the sake of brevity, I'm going to focus on just this one. This is an artist's impression of Kepler 186f, the first Earth-sized exoplanet found to orbit in the habitable zone of its host star. It was discovered by Kepler 10 years ago. The habitable zone is the range of distances from a star where a planet could have liquid water on its surface. We use that definition because we think that liquid water is the best environment we know for the chemical reactions that allow life to emerge and diversify. But do these planets actually have liquid water? Do they have life? The sad truth is, for Kepler's planet, we will never know. They are just too far away from us. So what we need now is to find exo-Earths in our cosmic backyard. That is, around stars near the sun. And I'm involved in 2 projects that aim to do just this in the coming 10 years. The first is the European Space Agency's PLATO mission, which will launch in 2026 and will use the transit method like Kepler, but with many small telescopes rather than one big one. And that allows it to look at much brighter stars nearer to us, but in a bigger patch of the sky. The beating heart of PLATO's science preparations, the science office, is located right here in Warwick. The other project is called the Terra Hunting Experiment, and it uses the Doppler method, which I introduced earlier, which allows us to search for planets even if they don't pass between us and their star. But star spots are even more of a headache for that method than they are for transits. And my group in Oxford specializes in developing advanced machine learning algorithms to get around that problem. Now, once we've found these planets, the next step will be to image them directly. That is, to separate the light of the planet from that of the host star. We can do that already, but only for planets which are much larger and on much wider orbits than the Earth. That's a movie of a distant planetary system. It was made by collating images taken by the Keck telescope on the island of Hawaii over a period of around 8 years. The light of the central star has been carefully modeled and subtracted out so you can see the planets. And because the light of the planets has been isolated, astronomers have then been able to take spectra of those planets, to split their light according to wavelength, and tell what molecules are present in their atmospheres. But the brightest planet in this system is 10,000 times fainter than its host star. The Earth, by contrast, is 1 billion times fainter than the Sun, so it's much harder. The Earth is also much closer to its star. And on this scale, it would be well within the black circle at the center of the animation. In fact, it would be within the little yellow star. So to image an exo-Earth, or several, hopefully, and take spectra of them, NASA is considering building a space telescope even more powerful than JWST, equipped with a coronagraph, which is a special kind of instrument that allows us to block just the star's light. If a technologically advanced alien civilization were to build such an instrument and point it at our own solar system from a distance of around 10 light years away, they would see something like this. And by taking spectra of those 2 faint blobs near the middle, they would be able to tell that there's something very, very special about the one on the right. While NASA is working on this concept they call HWO, the Habitable Worlds Observatory, the European Space Agency is investigating an alternative idea called the Large Interferometer for Planets, LIFE. It uses 4 separate telescopes, each flying on their own satellite, in incredibly precise formation so that the light of the 4 telescopes can be combined in a way that cancels out just the light of the central star. Both of these projects will not be launched before around 2040. We don't know which one will work better. There's many technological challenges to overcome, and the price tag will be significant. But the entire astronomy community is getting together to make it happen, together with engineers and administrators. And the reason we're so excited about it is all to get spectra like these. Here are spectra of the terrestrial planets in our own solar system. From the bottom to the top, we have Venus, the Earth, and Mars. They all show light emitted in the infrared by the interior of the planet, and then the dips are caused by molecules absorbing some of that light as it comes out. So we see carbon dioxide in the atmospheres of all three planets, but only the Earth also has water vapor and ozone. The water vapor tells us that the Earth has large amounts of liquid water on its surface. It has oceans. The ozone, together with the other molecules, tells us that there's something on Earth that must be producing large amounts of oxygen all the time. And that something, of course, is plants. We call such a combination of molecules a biosignature, because it can only be produced, as far as we know, by life. If we found a biosignature like this in the spectrum of an exoplanet, that would be compelling evidence of extraterrestrial life. Not necessarily complex or sentient, but life nonetheless. 2040, that can seem a long way away, and you might think an individual scientist working on these major international projects feels like a small cog in a big machine, but it's not like this. There's actually a feeling of belonging and of community and of being part of a shared adventure. And you can be part of that adventure too. There's one transit space mission I haven't mentioned yet. It's the one that's taking data right now. It's called TESS. It's found hundreds of exoplanets. But try as we might, our pipelines just don't detect all the transits. And sometimes human eyes are better than computers at finding patterns in data. So that's why we started a citizen science project where we ask members of the public to help us find planetary transits in TESS data. So I encourage you to have a go and experience the joy of finding a previously unknown world just for yourself. Thank you.